our next speaker is Professor Tassos Sextos. He is a professor of earthquake engineering at the University of Bristol in the United Kingdom. He's the head of the Earthquake and Geotechnical Engineering Research Group and the academic co-lead for the design and delivery of the new 15 million euro soil foundation structure interaction facility. Professor Sextos has an extensive record of service to the earthquake engineering community. We really look forward to your presentation and thank you for joining us at what must be an odd hour for you.
Not really, it's 5 p.m. So thanks very much. Thanks very much, Sari, for the kind introduction and everybody for attending. It's a great pleasure. It has been a very interesting webinar so far. I really enjoy. So I'd like on my side to share some thoughts with respect to the quantification efforts on seismic resilience for infrastructure communities based on work that we have done in Bristol. All the speakers today have highlighted how complicated this quantification is given the connectivity of our infrastructure and also the vulnerability of all assets that are exposed to seismic hazard and all other sorts of hazards, which can, extend from floods to even snowfall, fires, man-made hazards, and several complicated and gathered issues that our structures experience on top of the obvious fact that they're aging continuously. So resilience has, as we all know, attracted great scientific attention, but at the time there are still things that we understand and we know. One very obvious thing, also highlighted by previous speakers, is that example from the Tohoku earthquake in Japan. The direct loss was it was huge, it was about 300 billion, but the indirect loss associated with a lack of performance of ports and airports and commercial life, social life, lack of access, hazardous materials release, all this was actually having a twice as high toll in terms of indirect loss. Another thing that we are aware is that this indirect loss accumulates with time. The time it takes to rebuild a bridge on the left or reopen the highway on the right accumulates traffic cost and social cost and similarly. So in some countries like in Japan, perhaps this is a bit efficient and the time is really condensed in terms of recovery. This was just 1 week, but we all know from experience that this is not the case in most of the situations worldwide. So question is that we need to assess, of course, functionality and not just structural integrity, and focus on network and community and not just on a single structure. Along the same line of thought, the work that I'm trying to discuss today is all the challenges and difficulties in trying to quantify our ability to restore this functionality at both levels, in networks and community and agents, in the minimum time and with the minimum cost. This chart, of course, is well known. I'm not going to describe this. However, the two key aspects is that we always aim to drop as less as possible, the residual capacity to be as high as possible, but this depends on agent, of course, and then the recovery rate to be as quick as possible. But then we've got several challenges. We need to quantify resilience. We need to assess social and financial impact. We need to see whether we can actually measure community resilience in some meaningful way. We need to find this residual capacity, engage with stakeholders, engage with people, and perhaps also optimize our decisions for multiple hazards simultaneously. Sometimes these are conflicting issues. And from a practical perspective, we need to remote, of course, harvest, process, and analyze big data, but then we need to make decisions out of them, because that's also a very great challenge and difficult. So 3 of the examples I'd like to discuss with you, jumping directly on the applications. One is an effort, a methodology and a case study and a software actually to quantify seismic hazard by seismic resilience by convoluting vulnerability with hazard and traffic analysis, consequence analysis, and structural health monitoring for a real case in Europe. And effectively, you can guess that all the items that I mentioned have to be properly modeled, starting from the network topology to hazard and fragility, and then a Monte Carlo scheme, and then traffic cost, and structural cost, and cumulative indicators. But like Greg just presented previously, somebody needs to set some resilience objectives. That can be loss, can be downtime, can be cost, can be whatever. But this resilience-based assessment and management of highways, in that case, needed some rigorous modeling of all the stages in the chain that I presented. So all this has been compiled into a software architecture in a MATLAB with appropriate GUI framework that was linked with a traffic analysis software. And I would like to mention, quite briefly, the challenges we faced. After, of course, we did the obvious, which is to model the topology of the critical components that can, break the operation of the highway, like bridges, roads, tunnels, slopes, and other joints that can disrupt traffic. Of course, one had to liaise with people from transportation engineering so that we were able to get data from the highways to model the links, model properly, map properly the restoration matrices into the ArcGIS map. Once these data are collected and they are plotted, structures need to be classified into different structural typologies in terms of their different fragility and performance for a given intensity measure. And that can be done pretty easily with respect to the experience that most probably a group might have. But then the challenge is how to quantify seismic hazard in a scenario-based approach, because this is not a case that we can apply a standard PSHA. We need to have a scenario basis for different hazard levels of a fault rupture, which has to be a point in space, because otherwise it is going to cross our network and influence simultaneously several different points. And then the intensity measure distribution in space has to be accounted rigorously for every different scenario. And this would bring us to a number of maps, a number of hazard levels, a number of seismic faults and segments per fault, intensity measure distribution maps, and then all this procedure needs to be taken into account in a Monte Carlo simulation to assess probabilistically whether a road will be closed, depending on the fragility of the assets, or not closed for every different map. And then this was integrated, like I said, into a software, feeding in fragilities that you can get from the literature, or you can define yourself, or you can do refined analysis. But the challenge here, of course, is to make a decision. You can even use a machine learning, like we've done in another case, to feed in several fragilities so that the system can pick and decide for a different portfolio bridge whether it should be used, which fragility should be used for each case. But clearly, this has a degree of imbalance, because for bridges we're very experienced. For slopes, for instance, this doesn't exist. And slopes are different also in terms of intensity measure that is relevant, and in terms of limit states. And analysis cannot be done due to the special extent, which makes things more complicated. So we introduced an analytical approach here. But again, like I have to confess, this is quite imbalanced between bridges and slopes. And then another challenge is to quantify with the stakeholder repair costs and restoration times, and how much it takes to recover, and then repeat this traffic analysis for every different damage scenario, and then open up the data to an external open source QGIS software, plotted in QGIS software program for analyzing traffic redistribution for every scenario of open or closed assets along the network. This, of course, brings every calculation in stages. You can see here that links can be red for every different scenario, and gradually in time, they will become green. But this means that in every different step, you need to recalculate traffic redistribution. And then, of course, you've got an instance in time of functionality, of direct cost, of indirect cost, and then you accumulate that, and you can plot at the end of the day, and I'm just gonna show just one final slide, a prediction for the stakeholder in monetary terms, let's say in euros in this case, of what it would cost you, for instance, if you do nothing for different hazard levels. This is the red line, no action, or the purple one, if you don't retrofit, but you just improve your recovery plan, so you reduce the repair times, or you can do even better if you retrofit the weak links, which would be actually the obvious thing to do in most cases, or even better, which is the wiser thing to do, if you retrofit the links with the highest impact. So this is a consequence analysis that has so much better performance in terms of meeting the resilience objective set previously. And then again, of course, the question will open, is it worth investing in a life cycle scenario? All these funds now to retrofit now, the weak links or the links with the highest impact, and get some benefit probabilistically down the road, or we'd better do nothing and just wait for things to happen, and this will be better socially, financially. In my opinion, the answer always depends on who bears the risk in terms of the stakeholder. It doesn't have an obvious mathematical answer to this question, my opinion. And then in terms of structural health monitoring, we extended this application by using shake maps to update our prediction, so that after an earthquake, we don't have a scenario, we have a real distribution of IM. And then this also applies to the spectral acceleration on the bridges that were monitored. You can see here satellite links on the bridges so that in case of energy disruption, we could still get signals and update our scenario so that the stakeholder knows probabilistically in terms of their given fragility, which bridges most probably have failed so that they can inspect them quite quickly. Now, some limitations that I'd like to share with you very openly. This methodology, this software assumed that the traffic demand was identical before and after the earthquake, which obviously is not true. So we repeated this exercise with different degrees of traffic culture disruption, if you like, because after an earthquake, we don't go to our work, we do a U-turn, maybe we go home. So we repeated this exercise and we see how sensitive seismic resilience assessment is if we actually introduce the variation of traffic driver's performance, if you like, agent performance during crisis. That is an important aspect that influences the OD matrix. Secondly, whatever we assume and predict is as accurate as our assumptions are in terms of fragilities. For overpasses, we need to do proper modeling. Now we enter this particular aspect of we can use the caltrans curves, but at the same time, in terms of fragilities, we've got nonlinearities, we have multiple and very complicated abutment types around the world. So this, particularly given that the backwall is sacrificial, requires some more refined assessment. At the same time, we know very well, and this is very important for both bridges and overpasses, that soil structure interaction is frequency dependent. The reason we actually don't model that is that frequency dependence cannot be easily translated in the time domain with the usual impedance functions. And also, if we want to model the entire holistic soil structure interaction system, this is going to be huge and prohibitive for Monte Carlo assessment. For this purpose, we try to hack it a little bit and introduce lump parameter models, mechanical analogs that are basically mapping an impedance function in the time domain, but they operate, in the frequency domain, but they operate in the time domain. So we can use them as a low order FE model that can be implemented quickly and efficiently in Monte Carlo simulations. And you can see here the extension for plastic analysis with a macro element that was also introduced. Is that important or not? Well, if we repeat the exercise for different damage states, with and without frequency dependence, we can see an error of almost 80% for soft soils, particular beach configurations, and particular frequencies. So it's not negligible. Therefore, when we do this analysis, we'd better have it in a balanced way. And the same with respect to multi-damage assessment of all our assets. It's not just a single damage, several damages. Directivity is also important. What I'm saying is that proper modeling is important. I'm not going to go into too much detail, but we need to make sure that whatever has influence on our prediction is modeled properly. And we made an effort to model this in to develop a software that incorporates all these assumptions into OpenSys so that this is kind of easy to do in an ordinary assessment without getting into too much the theoretical background. The second application I'd like to show you is how our computations were linked with experiments in light of hybrid simulation. Of course, I'm not bringing any news because hybrid simulation is around for many years. And this is just a simple, let's say, highway bridge that we tested a few years ago, physically and computationally. The reason I particularly show this is because when we try to do this between Europe and the States, yes, this is standard technology, we know how to do it, but the main challenge is the latency when crossing the Atlantic. It's almost 100 milliseconds. Therefore, this is just to advocate for the necessity for better internet connection, better 5G probably, or dedicated lines that can perform real-time hybrid simulation between Europe and Asia and the States in order to combine computational and experimental frameworks. Second example I'm going to share with you is an effort to translate whatever we did for highways, exactly the same concept, for pipelines. Here the challenge is twofold. A, the fragility curves are super simplified because they're actually repair rates. And the reason is that due to the extent of the pipelines, water or gas, it is very difficult to model them rigorously. So this exactly has led to the perception that earthquake multiple, especially variable ground motion, has zero effects on pipelines. So we did a very large computational model to see whether this is true when soil changes properties, which was not true for bridges, and it's actually not true for pipes as well. And in that case, we substructured the system between the far field and the near field, and we did quite a rigorous simulation, including buckling of the pipe due to differential axial strain and soil pipe interaction, introducing friction at the interface, and all that. At some point, that's the open question. Do we really believe our analysis, or we really have to apply some experiment to see whether that's valid or not? Because analytically, we've seen that the regulations actually suppress the possibility that differential strains can buckle the pipe. But truth is that both numerically and experimentally, as we checked by using a soil box on our shaking table at the University of Bristol, it was actually shown and measured by fiber optics along the pipe length that this would be the case if soils change abruptly properties in space. And these are the pipe axial strain that correspond to pretty much 60 or 70% of critical buckling load. And if we change the scale to real scale, yes, it can buckle. So the question is, do we stick to the analysis, or we really do have to do some testing? That's an open question, of course. Similar problem when we've got a pipe in a pressurizing station connecting two buildings. These two buildings, in that case, effectively have different dynamic properties, and they are linked with a connecting pipe. We model that numerically, but then we substructure it between physical and numerical testing. And what we found out was actually that the influence of the connecting pipe can harm both the structures and the pipe itself. By doing this substructuring and hybrid testing, we repeated that the physical test was at the University of Patras, the rest was at the University of Toronto and the University of Bristol. At a glance, you might think that that's not a hybrid test. But the truth is that the dynamic properties of the two buildings actually change as the connector is getting damaged because it's a coupled system. Therefore, with this hybrid test, again, it's actually verified what we could predict numerically. Going to my final example, because Seth said previously that resilience is all about people, and actually I fully agree. So I'll take you to the most humble version of resilience we've done, skipping some interesting tests that I could show. But I would like to share with you an effort to quantify resilience for the school communities in Nepal in collaboration with the World Bank and Asian and American universities. And actually show something that's very basic. It's a humble, smart application to inspect buildings and assess community resilience. Now, this again seems to be something very simple, and we could easily use the FEMA guidelines. But the problem is that the probability of collapse that we can get from European or US standards is not applicable for Nepal. We've got 39 structural typologies. We've got a scarcity in data. We have huge uncertainty in construction practices. So in order to predict fragilities and probability of collapse, we need to gather data. The best way we found to do this was to liaise with the World Bank and develop empirical fragilities of masonry school buildings based on the post-earthquake data that were very rigorously and carefully collected after the Gorkha earthquake. Secondly, because we didn't have information about the soil, we had to do our own drills in the Valley of Kathmandu to collect geotechnical data, rebuild everything we could find in the literature in a geodatabase in 2D and 3D form so that we could present these VS maps and do microresonation studies that could help us understand a little bit more about ground excitation. But then again, in terms of materials, what kind of values can we use for the fragility analysis? We had to do our own testing, material testing, wall testing, and not just one or two of them. We had to repeat 10, 15 structural build and test, structural walls on site, so that at least we can assess the dispersion of the material properties for different structural, cultural, let's say traditional typologies. And then this was presented and integrated into a mobile app. You can see here the mobile clients through a firewall, they feed data into the server. The app is pretty simple. It asks specific vulnerability items, hazard and soil properties are input automatically given the GPS location. And then this information is fed into the GUI of the web app, which doesn't require any software, but the stakeholder, in that case, the Ministry of Education of Nepal, is able to assess which are the buildings. We've got already more than 500 school buildings assessed, which are the buildings that should be prioritized in terms of risk. That is both hazard and vulnerability and exposure. And we have released that for the benefit of the Ministry of Education. And the two final slides are related to a twin application we developed for assessing the community resilience. Now, this, you can see the English version, but this has been developed in Nepali. local language, and we have more than 120 questions that we developed along with our NGOs, but we worked in the field. And we ended up by assessing and quantifying a number of factors that affect the ability of a community to have the capacity to respond to a natural disaster. This is presented in the form of a self-assessment tool. So every year, it's not governed by the education ministry. Every year, a single school can relatively assess its capacity. So a few final comments, if I may. Going back to our initial discussion. Can resilience be quantified? I think yes, but we also need to have a balanced rigor in assessing uncertainty among all aspects that influence resilience. Secondly, community resilience is clearly multidisciplinary and multi-hazard, and sometimes the objectives are conflicting. So we do need a holistic framework that convolutes computing and testing and probabilistic assessment and smart tools. Computational power, in my opinion, is not enough. We need some intelligence, particularly to fill some gaps when we don't have information. And big data is huge, but again, perhaps we need to make sure that we make sense out of this data. They are clean, they're reliable, we can make decisions with them. What next, in my opinion, is to integrate further these models into appropriate risk and loss models towards resilience-based asset management to improve our residual system capacity, because this is what we can do before the next earthquake, and invest in low-cost retrofit of infrastructure. Create awareness, think smart, think complicated, but the procedures need to be simple for the governance. Thank you.
Thank you, Tassos. Very interesting presentation. You covered a lot of ground in many different fields and disciplines. There is one question that I see here, and this is from David Bonowitz. It says, regarding the app for inventory of URM schools, is this the tool that Building Change is using?
We are in collaboration with Build Change, yes.
Okay. I have a question myself. You have covered like the response of different types of infrastructure systems. They come from different disciplines. And I asked a similar question to Seth Goikema as well. How do you get the models from those systems? Do you, or different disciplines, do you develop them yourself and then link them with what you're doing? Or do you get collaborators from over those fields and then work with them?
Well, that's a very good question, actually, Sheriff, because I think that when shifting from one discipline to another, or from one type of infrastructure to another, there must be a common basis of understanding and mathematical framework, but there is always need to liaise with different disciplines in order to contextualize what you're doing for the appropriate industry. So from project to project, from effort to effort, we always engage industrial partners, stakeholders, and regulators that are relevant to the context. We aim to apply our probabilistic or computational tools so that we make sure that whatever we develop is co-produced and useful.
Okay. Well, thank you very much. Are there any other questions? I'll just wait for a second in case someone is typing.
Just to say while waiting, if I may, that I think based on, I try to show you different things and not stick to one particular aspect of what we are doing, because I think we should see resilience as a whole. And resilience, when we're talking about infrastructure, it is not just one type of structure. I've shown examples where for bridges we're very well, or at least our group, we are familiar, but for the science in other disciplines that affect resilience is not balanced. And at the same time, the challenge is always to have impact at the agent level. This requires a multidisciplinary work with several scientists. I would even mention social scientists, people with finances background. The problem is bigger than us. And I don't want to pretend that we know how to solve it. We need to liaise with others.
Indeed, and you know, that is the primary motivation for this workshop, is to kind of see how computation can allow us to do exactly what you're saying. I personally think that working across the disciplinary boundary is hard, just because the language is different, the method of research is different, the logic for research is different. But when it comes to computation that we all do, it just seems that that is a natural language which we should all be able to understand. And the thing becomes, how do we leverage that to be able to achieve what you said? So certainly that's a really important question, Professor Sextus. There's another question from Mustafa Badruddin. He's saying, very nice presentation. Would you please elaborate more on social metrics that have been considered in resilience quantification of the school case study?
Okay, first we can recall that we contextualize this work to a developing country, right? This is not, it is similar to what makes our cities resilient, but it is in a way different. For the case of Nepal, we identified 12 resilient factors. In essence, they were about awareness, preparedness, connectivity. For instance, there can be a single slide on the mountains that can disrupt the connectivity and the ability to share resources between two different villages, just to mention an example. Allocation of resources, previous experience, governance, how the communities culturally are used to work together. And I have to say that in these countries, there are some things, there is some hidden capacity, some overcapacity, if you like, in developing countries that don't necessarily exist in our developed world, because they are more used and trained to share. And this builds a degree of redundancy in their community resilience. So yes, there is a set of 12 metrics that we identify. And interestingly, questions are asked not just to the headmaster of the school, but also to parents, teachers, and kids in Nepali. And very interestingly, the resilience feedback that we get from kids in Nepal was quite different in some cases with what the adults thought about how well the community was working.
A question from Eric Mershman. With your community resilience metrics, how do you effectively measure the performance and recovery of a community as a whole?
That's a very good question, actually. And I would like to stress the word measure. Maybe it is better to say we assess. However, like I said, it's not about absolute metrics. The assessment is relative. So the community is asked to do this test, which also includes some automatic advice every year, like, do you do this test? We see that you're not well connected in this and that terms with the central government. You should be doing 1, 2, 3. You get a score, and next year you repeat that and you get another score. So this performance is relative, and it has to be relative, in my opinion. It means nothing to give an 84.34 percentage score to a community.
There is one last question, and then I think we have to stop to switch to the next speaker. This is from Ji Jin Yu. Says, great presentation. Can you please tell us more details about the model of simulation and experiment of the pipeline to simulate the different types of hazards like soil liquefaction and fault slip?
Okay, this is a great question, because actually the transient analysis under traveling waves, which, as I said, normally they don't produce damage on pipes because pipes are very flexible and of low mass. They only do that for varying soils, is different than post-transient liquefaction or fault slip, which is static loading and not dynamic. So in our model, we predict different fragilities for different types of geohazards, and then we convolute the risk.
Thank you very much. Professor Sextus, once more, thank you very much for joining us.